Hello and welcome to the first in a series of online lectures that we'll use to finish up Chemistry 1101 in the spring semester of 2020. In today's miniature lecture, we'll continue in Chapter 8 and hopefully finish the material on intermolecular forces. So just as a very quick review, we call it intermolecular forces are these attractive forces that exist between molecules. And we talked about before in your notes, you should have information discussion about three types of intermolecular forces, the so-called dipole-dipole forces. These are the forces that exist between all polar molecules. This is when the partial positive end, the permanent partial positive end of one polar molecule is attracted to the permanent partial negative end of a adjacent polar molecule. You also have hydrogen bonding intermolecular forces, which is a type of dipole-dipole intermolecular force, but it's sort of a special type, a especially strong dipole-dipole force. In order to have this IMF, the molecule must have a nitrogen hydrogen, an oxygen hydrogen, or a fluorine hydrogen as part of its structure. And finally, we have the London dispersion forces, and these are IMFs exist for all molecules, and these are the only IMF that exist for non-polar molecules. So these are relatively weak IMFs because they exist between the temporary partial positive end of one molecule and the temporary partial negative end of a adjacent molecule. But for non-polar molecules, this is all they have. But even though these are relatively weak, they do increase with increasing size of the molecule, increasing molar mass of the molecule. So going back to generate this discussion about IMFs, we had discussion of three common substances, table sugar, water, and chlorine, that exist at different physical states, solid, liquid, or gas, even though they're all at the same temperatures. They have the same amount of energy, but one exists as a solid, one exists as a liquid, and one exists as a gas. And the reason has to do with IMFs. The fact that we look at their structures, you can see that sugar, table sugar, has a very large molecule, has lots of OH groups to it, so it can hydrogen bond, and it can hydrogen bond quite extensively. So it has relatively strong IMFs, which is why, at room temperature, it exists in the solid phase. Water is also a polar molecule like table sugar, but it can only hydrogen bond 2 times, so it has relatively weaker IMF, so it's a liquid. And then chlorine gas is a non-polar molecule, so it has weak IMFs, which is why it exists as a gas at room temperature. We can use our another IMF decision tree, to be able to determine what types of IMFs are relevant for a particular molecule. First question is the molecule polar? If it's not polar, then the only conclusion we could draw is it must have just those weak London dispersion forces. But if it's polar, then there's a second question we have to ask ourselves, which is, according to the structure, does it have either hydrogen-oxygen bond, hydrogen-nitrogen bond, or hydrogen-fluorine bond? If it doesn't have any of those structurally, then it has London dispersion forces, and because it's polar, it also has dipole-dipole forces. But if it has any of these structurally, like we saw in the previous slide for sugar and water, then it's going to have all three: London dispersion forces, dipole-dipole, and hydrogen bonding. So please note that if the question, as we'll see in the next slide, is what types of IMFs are relevant for a molecule, these are your 3 possible answers. It's either just London dispersion forces, if it's a nonpolar molecule, London dispersion forces and dipole-dipole, if it's a polar molecule that can't hydrogen bond, and it's all 3, London dispersion forces, dipole-dipole, and hydrogen bonding, if it's a polar molecule that can hydrogen bond. So to practice what we just referenced, being able to determine for a given substance what types of IMFs are present, we have these 5 examples. And just to keep things as simple and straightforward as possible, unless we're given electronegativity values, so in other words, we're allowed to calculate that difference, and then from that difference, decide whether a particular bond is polar or nonpolar, we can assume that for simplicity's sake, that all bonds between 2 atoms are going to be polar, except for 2 important exceptions. One is bond between the same 2 atoms, so carbon-carbon bond or a hydrogen-hydrogen bond or a bromine-bromine bond doesn't necessarily going to be nonpolar. And very commonly, very importantly, the carbon-hydrogen bonds are also going to be nonpolar. So using these assumptions, let's decide what types of IMFs are present for these molecules. So we have HBr, it's a diatomic molecule. Diatomic molecule just has one bond. That one bond, what that bond is, makes the molecule. So we can assume that that bond is polar, because it's not one of the exceptions. So the bond is polar, the molecule is polar, but we don't have a hydrogen-oxygen or hydrogen-nitrogen-hydrogen fluorine bond. So that means it just has London dispersion forces in dipole-dipole. For CH3, CH2, CH3, a molecule called propane, just carbon-carbon bonds, carbon-hydrogen bonds, makes it a nonpolar molecule. Nonpolar means we just have London dispersion forces. For this molecule, ethylamine, we have this nitrogen-hydrogen into it, which is going to give us polar bonds and therefore also a polar molecule. So we'll have London dispersion forces, as all molecules do. Because of this, we'll also have dipole-dipole forces, and because we have a nitrogen-hydrogen bond, we actually have two nitrogen-hydrogen bonds, we'd also have hydrogen bonding. For argon, it's an atom. Atoms are always nonpolar, so we just have London dispersion forces. And then finally, iodine. Iodine is a molecule composed of two iodine atoms that bonded by one bond. That one bond is nonpolar because we have same two atoms involved, so the molecule is nonpolar. As a result, we have London dispersion forces. So notice that these last two, argon and iodine, they both have London dispersion forces, both have relatively weak IMFs, but between the two, we'd expect that the IMFs for iodine, its London dispersion forces, should be a lot stronger because it's a much more massive molecule. It's a much higher molar mass than the argon atom has. Consequently, even at room temperature, even though argon's a gas, iodine is a solid. Once again, another consequence of having strong IMFs versus having relatively weak IMFs. And then one consequence of comparing IMFs, one way we can predict some of these, at least relative physical properties of these substances, is we're looking at the boiling point. The boiling point has to do with the temperature which a substance goes from the liquid phase to the gaseous phase. In order for that to happen, the molecules in the liquid phase, they have relatively moderate IMFs, so those IMFs have to break in order to give us the gaseous molecules that have essentially no IMFs. And so the stronger the IMFs, the higher the boiling point the substance will be. So the boiling point and IMFs are related to one another in that way. So really the question is, which molecule is higher boiling point? Really the question is, which molecule do we expect to have the stronger IMFs? And so between CH4 and C3H8, we have two molecules that are both nonpolar, both carbon, and only contain carbon, consists of carbon and hydrogen. So they both have just London dispersion forces. But between the two, because C3H8 is more massive, has a much higher molar mass than CH4, almost 3 times as massive, we'd expect then that C3H8 would have overall stronger London dispersion forces and therefore a higher boiling point. So C3H8 would be our answer for this example. For CH3NH2 versus CH3CH3, CH3CH3 is another nonpolar molecule. Methylamine, though, is a polar molecule that can hydrogen bond. So even though they're approximately the same size, CH3NH2 has not only London dispersion forces as CH3CH3 does, but also it has dipole-dipole forces and hydrogen bonding. So overall, this molecule is much stronger IMFs, and consequently, it's going to should have a much higher boiling point. CH3F versus CH3CH3. CH3CH3 is another nonpolar molecule. CH3F, though, we need to be careful about. Draw this quickly. CH3F would have this structure. So yes, it does have hydrogen and fluorine. We've seen this example a few times before. Now leave off the lone pair electrons. But even though it does have carbon, fluorine, hydrogen, we don't have a direct hydrogen-fluorine bond, so it's a polar molecule, but it cannot hydrogen bond. But in any case, we have both aligned perfect forces, but CH3CF also has dipole-dipole. So CH3CF would be stronger IMFs. And I think finally CH3Cl versus CH3OH. CH3Cl, similar to this structure, except we have a chlorine here, so it's still going to be a polar molecule. CH3OH is also polar, but the difference is that because it has OH, because its structure, draw this quickly here. So instead of the chlorine atom, we'd have an OH group here. Again, leaving off the lone pair electrons. Because it has this OH group attached to it, that's going to allow it to do hydrogen bonding. So even though they're both polar molecules, this one to have overall stronger IMFs because it can hydrogen bond, whereas this one cannot. So CH3OH would be our answer. Cool. And then finally, looking at density. So generally speaking, the strength of IMFs is proportional to the density. IMFs are attractive forces going to try to bring the molecules closer together. And if the atoms and molecules are closer together, then you can have more mass, more atoms in a given volume. So therefore, for the density, that ratio of the mass to volume is going to be larger, going to be higher. And so we can see that with methane versus propane, two nonpolar molecules we looked at in a previous slide. The difference is their molar mass. As a consequence, the boiling point of propane, as expected, is higher than that of methane, and also the density of propane is also higher than that of methane. So generally speaking, as the IMFs increase, the density is also going to increase. Important exception, though, so because of that, solids are generally going to be more dense than their liquids, have moderate IMFs. A very important exception, though, is water. Solid water is actually less dense than liquid water. And the reason has to do with when you have solid water, when water freezes, becomes ice, when molecules slow down, they want to maximize all of those IMFs, especially those hydrogen bonding, those very strong IMFs that bring these molecules and attract these molecules to one another. So because of water structure, because of water's even shape, we find that when solid water forms, it maximizes those hydrogen bonding networks, those hydrogen bonding IMFs, by forming this type of structure, this more hexagonal or six-sided structure. And this, of course, occurs in 3 dimensions. The thing to take note of, though, is notice how much empty space there is between these rings of water molecules. More empty space, a larger volume is going to lead to a lower density. And so even about the same temperature, solid water ice is about 10% less dense than that of liquid water. As a consequence, because of that, and this is very unusual, even though it's something we see every day, it's very unusual for substances, solid water, ice, actually floats on liquid water, as we know. Every other substance, in the solid form, liquid form, the solid form would sink into that liquid form. And one of the very important consequences of that is that during the wintertime, when ice freezes over, it only freezes over the very top of the lake. And so the lake will freeze over, but the top of the lake will form a nice thick ice sheet. But underneath that, it'll be very cold, but it won't be freezing. And so that allows, even during the harshest of winters, that allows the fish and other aquatic life to live and survive the winters and then come back in full force in the springtime. Then also another interesting consequence of that is that these snowflakes, of course, are unique, but they all have intrinsically sort of a hexagonal structure to them because the water molecules that make up those ice crystals, those snowflakes, also have this hexagonal structure to them. So it's an example of what we can see macroscopically mimicking or a result of what's happening microscopically. So what we can see compared to what we can't see, have to imagine must be happening. So with that, we finished up our discussion of intermolecular forces. And our next lecture, we'll talk about gas laws and gases, behavior of gases, what happens when molecules don't have any intermolecular forces.